So friends, hello friends, welcome my channel. Today's discussions is manifold theorem and differential geometry. So friends, we will just discuss briefly manifold theorem and also we discuss history, and after that we will discuss covariant and contravariant vectors. So friends, this lecture is very large because we will discuss a lot of topics. So let's start to discuss history of. So friends, when we will discuss history of differential geometry. So friends, first we need to learn Euclid geometry. So friends, Euclidean geometry, the study of plane and solid figures and solid figures on the basis of axioms and theorems employed by the Greek mathematician Euclid proposed five common notions such as things equal to the same things are equal. Five unprovable postulates. Five unprovable postulates. After that, friends, we get non-Euclidean geometry. So friends, Euclidean geometry, you will see that school level we study this kind of geometry, class 8, 9, 10 in a lot of school level. But non-Euclidean geometry named hyperbolic geometry is then obtained as the geometry of the connected two-dimensional complete space. So friends, suppose this is a straight line. This is a straight line. So friends, according to the Euclid geometry, in case of real physical world, it may not be a straight line. It is not straight line. So friends, we get a trouble. So we see that Euclid work. So we get that Euclidean geometry is not in case of physical world. So friends, Riemann create a geometry. This is called Riemannian geometry, where he explored manifold, Riemann manifold and differential geometry get birth. So friends, differential geometry get birth and Riemann manifolds and differential geometry get birth. It is based on tangent and space and curved surface. Riemannian geometry, Riemann created a geometry So friends, Riemannian geometry studies Riemannian manifold, smooth manifolds with Riemannian matrix. Riemannian matrix. So friends, you see that Riemannian geometry studies Riemannian manifold, smooth manifolds with Riemannian matrix. This is concept of distance expressed by means of smooth positive definite symmetric bilinear form defined on the tangent space at each point infinitesimally. That is in the first order of approximations. Various concepts based on length, such as the length of curves, area of plane, regions, and volume of solids, all possess natural analogues in Riemannian. Now, this is the note. A distance preserving diffeomorphism between Riemann manifolds is called isometry. Number 2, non-Euclidean geometry named hyperbolic geometry is then obtained as the geometry of connected two-dimensional complete space. General relativity is the most famous application of non-Euclidean geometry and differential geometry. Near a massive object, general relativity shows the geometry is not Euclidean. So friends, whatever we have learned at first, we have learned that Euclidean geometry is the first primary geometry, and after that it is developed step by step. We get non-Euclidean geometry. After that, we want to express in the physical world. We need to express every geometrical shape in physical world. We use differential geometry, friends, and differential geometry is the most important geometry in modern science. And we see that general relativity is the most famous application of non-Euclidean geometry and differential geometry. Near a massive objects, and general relativity shows the geometry is not Euclidean. It is not Minkowskian. So friends, let's start a small brief discussions about Riemann manifold. So friends, Riemannian manifold in differential geometry, Riemannian manifold space Riemannian manifold space M, G. G is a real smooth manifold M equipped with a positive definite inner product. Positive definite inner product GP on the tangent space TPM at each point P. A common convention is to taken G to be smooth, which means that for any smooth coordinate chart Ux on M, the n square function G del by del x to the power I del by del x to the power j such that U tends to R smooth function. So friends, we need to learn Riemann manifolds because it is very interesting. Now friends, we need to know what is coordinate chart. So friends, coordinate chart defined on a set X is a subset. A set X is a subset U of X, that is U proper subset of X together with the bijection phi such that U tends to phi U subset of r to the power n. Phi U and open set phi U of r to the power n points X of U are determined by n coordinates. So friends, I have discussed very briefly about Riemann manifolds. Now I want to discuss Einstein summation convention definition. So friends, Einstein summation conventions is very simple, but whenever index, subscript or superscript, index or subscript or superscript. So friends, subscript means like AI. This is called subscript. And suppose A to the power I, this position is called superscript. Is repeated in a given term. Summation should be done over that index from 1 to n unless otherwise specified. This is called summation conventions. So friends, I write the definitions. Whenever an index, subscript or superscript is repeated in a given term, summation should be done over that index from 1 to capital N unless otherwise specified. This is called summation convention. This is called summation convention. And now example, according to summation convention, dx superscript I del, we discussed that I is equal to 1 to capital N del x to the power I divided by del x bar coordinate to the power alpha into dx bar alpha can be written this way: del xi divided by del x bar whole to the power alpha into dx bar whole to the power alpha. So friends, this is the, I can write this way. And another way is dx bar alpha coordinate are two coordinate, one is bar coordinate, another is simple coordinate. So dx bar to the power alpha is equal to del x bar to the power alpha divided by del x to the power I into d x to the power I. So friends, this is the way of the summation conventions. We do not use summation symbol. Let's discuss dummy index. If an index is repeated in a term so that summation over it from 1 to n is implied. Such index is called dummy index or umbral index. Umbral index. Now we discuss free index. According to some, if an index appears only once in any term, it has a definite value. Any value between 1 and capital N, such index is called free index. So friends, we discuss free index and dummy index. Let's see one example in here. Now we discuss in here. We see dx to the power I, dx bar alpha, d superscript I, and dx bar alpha and x bar alpha. So friends, you see that alpha and alpha both are twice. Alpha appear twice. So it is dummy index. And now I is appears once. So it is free index. I hope I can clear this concept, friends. I think that I can clear this concept. What is dummy index, what is free index, and summation conventions, everything I hope I can clear. Now let's start to discuss Kronecker delta. Since x to the power I is r independent of each other, d x to the power I divided by d x to the power j equals to 0 if I does not equals to j, equals to 1 if I equals to j. And we define the Kronecker delta symbol. We define the Kronecker delta symbol as del ij equals to 0 if I does not equals to j, equals to 1 if I equals to j. So in unbarred coordinate system, we can say del ij is equal to d superscript I and d superscript j. Similarly, in bird coordinate system, x bar whole to the power alphas are independent of each other, are independent of each other, and hence we can write del alpha comma beta is equal to d x bar whole to the power alpha into d x bar whole to the power beta. Again x subscript I as are function of x bar whole to the power alpha, so dx superscript I and dx to xx superscript j is equal to del x I superscript I del x bar superscript alpha and del x bar superscript alpha divided by del x j, or del ij equals to del x to the power I del x bar whole to the power alpha into del x bar whole to the power alpha divided by del x superscript j. This coordinate is called unbarred coordinate system. So friends, let's start to discuss transformation by contravariance and contravariant vector. So let's take 2 point p is equal to x superscript 1, x superscript 2, x superscript 3, x superscript n. That implies unbar coordinate and q, this is the p equivalent to, and q equivalent to x superscript plus d x superscript 1, x2 plus superscript d x2, x3 plus superscript d x superscript 3 up to up to xn x superscript n plus d x superscript n. And coordinate of bar coordinate system coordinate of bar coordinate system system P equivalent to x bar superscript 1, x bar superscript 2, x bar superscript 3 up to dot 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 x bar superscript n, and q equals to x bar 1 d x bar 1 in superscript 1 and x bar 2 plus d x bar 2 plus dot 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 x bar n plus d x bar n. This is the formula, friends. And now the relation between two systems of coordinate, one is barred and another unbarred. The relation between two system of coordinate coordinates B x bar superscript I x bar I superscript x superscript 1 x superscript 2 x superscript 3 up to x superscript n. This is the relationship between bar coordinate and unbarred coordinate. Now I can write dx bar superscript I del x bar I del x to the power 1 into del x to the power 1 plus del x bar I divided by del x2 into del x2 plus del x bar I divided by del superscript n into del superscript n. So friends, this is the another, and by the Einstein summation convention it can be written del x bar I divided by del x to the power alpha into del x to the power alpha. This is the summation convention. Summation convention, and transformation is a small increment in system of coordinate. Take some quantity like a1, a2, a3 up to an. This is some quantity I take. So in the quantities, and these quantities is the bar coordinate. And a bar 1 and a bar 2, a bar 3, this is the bar coordinate, sorry, it is unbarred coordinate, and this quantity is bar coordinate. So friends, a bar I is equal to del x bar I is equal to del x to the power alpha into a alpha. This is the component of contravariant vector. This is the component of contravariant vector. Now we want to discuss covariant vectors. Covariant vector. Covariant vectors, let phi is equal to phi x superscript 1, x super 2, x super 3, x super n, and del phi by del x1 del x1 del phi divided by del x2 up to del f del phi by del xn exists, and del phi also bar, this is the bar coordinate, and del phi divided by del x bar 1 and del phi divided by del x bar 2 up to del phi divided by del x bar n exists. This is the unbar, this is the unbar coordinate, and this is the bar coordinate. Now x superscript I is equal to x superscript I super I is equal to, can be written x bar I, x bar 2, x bar 1, x bar 2, x bar 3 up to x bar n. Del phi divided by del xi x bar I is equal to del phi divided by del x1 into del x1 divided by del xi plus del phi by del x2 into del x2 divided by del x bar I plus up to del phi divided by del x to the power n into del x to the power n divided by del xi, del x bar I. So friends, it can be written this way: del phi del x bar I is equal to del x to the power alpha divided by del x bar to the power I into del phi divided by del x to the power alpha. This representation is summation convention. Summation convention. This is called covariant. This is covariant. Covariant. Now friends, take some component A1, A2, up to AN and A bar 1, A bar 2, up to A bar N. This is the unbarred component or unbarred, and this is the bar coordinate. So friends, how can I write? I can write this is the representations. A bar I is equal to del x to the power alpha divided by del x to the power I into A alpha. This is the covariant component. This representation is covariant component. Let's start to discuss that matrix representations. So how can I write it matrix in matrix represents? So at first I write it like a equation type. In here A bar I can be written del x 1 divided by del x to the power I into x bar I, this x bar I into A1 plus del x to the power 2 divided by del x bar I into A2 plus up to del x to the power n divided by del x bar I n. So friends, this is the AI. So I can write this way: A1 is equal to del x to the power x1 divided by del x bar 1, and it can be written A1 plus del x2 divided by del x bar 1 A2 plus del x superscript n divided by del x bar 1 equal to A n. Similarly, I can write this way: A2 is equal to del x to the power 2 divided by del, it is not 2, it is 1, x bar 2 a2 plus del x to the power x superscript 2 divided by del x bar 2. It is a1 and this is a2 plus del x 3 divided by del x bar 3 into a3 plus up to plus del x to the power n divided by del x bar, it is not 3, it is 2, x bar 2 into an. So this is the type. This is the last term, an can be written del x to the power 1 divided by del x bar whole to the power n a1 del x to the power 2 divided by del x bar n a2 plus up to dot dot del x n up to divided by del x bar n into an. So friends, it can be represented as the matrix type. How can I write it? I shall go it. This is the matrix representations. A1, A2, A bar 1, A bar 2, dot 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 up to A bar n divided by del x1 divided by del x bar 1 del x2 divided by del x bar 2. Sorry, not x bar 1, it is x bar 1 del x3 divided by del x bar 1 up to dot 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 del xn divided by del x bar 1 and del x1 divided by del x bar 2 del x2 divided by del x bar 2 del x3 divided by del x bar 3 up to dot 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 del x to the power n divided by del x bar 3. This way I can write, and it can be written also this way: del xi divided by del x bar capital N del, so it is 1 not I, del x2 divided by del x bar capital N and del x3 divided by del x bar capital N dot 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 up to del x to the power n divided by del x bar to the power n. So friends, and after that it should be multiplied by a1, a2 up to ak. So friends, this is the very long lectures. I hope that I can clear this concept. So please practice and try to understand everything. This is very conceptual and very interesting. Differential geometry is very interesting topic. I hope you like my lectures. Thanks for watching.